you want to get to like the same side as you started on, you have to go to. You can't. It has to be.
Right. After doing an even number, after following an even length walk, where am I always?
On the same side.
Back on the same side, right? And so I can't complete it now because I'm not allowed to go back to my original vertex yet. Who's with me? Okay. And now what? And now what would we sort of do next? If we're that didn't work. So I guess I have to go back to B, right? So okay. Well, if I go back to B, well now can I go back to that vertex in A that I'm trying to complete the cycle on? Well, I could, but again, then it will be even, right? This is a super sort of crappy informal, but this is sort of at least makes it sort of clear that you can't have an odd cycle, because to have an odd cycle, you would have to like always be connecting two people from the same set of the bipartition. That just doesn't work. All right, that proof's like decent, but no, man. I want to I want a real proof. I think the rigor actually helped. At least it helps me a lot. This is due to something I found on the internet. Let's go. Let G be bipartite. In other words, let G be a set of vertices and a set of edges, and let A good. Let A and B good. Let A and B be the sets of the bipartition. In other words, let A and B be sets of vertices such that the union of A and B is the set of all the vertices, and that A intersect B is empty. In other words, the division of the set of vertices into A and B is a partition, and furthermore, it is a bipartition. Who's following all this technical language? I think it's to me it's helpful. Well, what does this just says that A and B partitions the set of vertices, but if it's a bipartition, then it's also true that all edges, we call these maybe epsilon, in the set of edges are of the form AB, where A is in A and B is in. This is just writing out the definition of bipartite, which is to say that a graph is bipartite. It's a way of splitting up into two sets, which is the entire graph, and every edge connects an element from one set to an element of the other. Good so far. Haven't really done anything yet. Okay. Now, we want to show that G has no odd cycles. Well, suppose G has an odd cycle. Cycle. Let's call that cycle C, and let's say it's of length n, where n is odd. N is odd. Okay. Why is this impossible? Well, first of all, let's just introduce a little bit even more notation. So if C is a cycle, what is a cycle really? A cycle is just like a walk that one takes from vertex to vertex to vertex to vertex that ends back where you started, yeah? Okay, so let C be like V1, V2, V3, etc. Eventually, well, we've already said that the cycle is of length n, so it'll hit Vn, and then finally back to V1. That's what this particular cycle is. Cool? Say cool. Okay. Wow. Okay. So without loss of generality, let's let V1 be in the first set A, and then V2. Well, then what can I say about V2?
Has to be.
It has to be in B. So well, so the V1 and V2. So V2 has to be in B because that's what it means to be bipartite. Every edge connects a vertex in A to a vertex in B. So V is in B, V3 is in A, and then etc. Thus, I now can give an explicit description of the kth vertex in this cycle. You tell me.
If K is odd, it's an A.
Yeah, if K is odd, then VK is in A, and if K is even, then K is in B. Woo, that's pretty good. Well, this was all, I haven't even done anything yet, right? I'm just like introducing enough notation to make everything I want to say sort of rigorous. Where does this all sort of go awry? Now I think the argument can kind of like begin, right? What can I say about, yeah?
If the cycle length is odd, then the final one has to be even. What?
The final one is the same as
Yeah,
the
right,
first.
because
N is odd. So,
VK is an A, which is the same as the beginning.
so V, are you talking about Vn then? Vn. Yeah, so what do I know about Vn? N is odd, well I've assumed from the beginning that N is odd, right? That this is an odd, this is specifically an odd cycle. So according to all of this analysis, which is sort of just kind of milking the definition, right? What do we know about Vn? It's in A. But V1 is in A. Uh-oh, this is just, that's it, man, right? So, okay, if you want to even add one more sentence, this is maybe a little bit unnecessary, but so what we have is that the edge, Vn, V1, is an edge of the cycle, okay, which means that Vn, V1 is an edge of the, is an edge of the graph. And that is a contradiction with the bipartiteness, bipartiteness of G. Okay, that was pretty straightforward. Let me just say that I've tried to do a proof like this, like using my own wits, for like years, and it just produced like crap. You know? So it just really is, really, there's a certain level of like sophistication in like how to set things up, which I think you just get from experience. I got it from internet. Woo! All right. I think Daniel Zhu helped too. Yeah, a little bit. So this one's like fairly standard, I think, but I think Gossett doesn't do a good job. All right. The other direction is, I think, more difficult. Does everyone agree that this was like the easy direction, right? I wrote it out nice and formally, but in some ways it was kind of like, okay, of course I can't have an odd cycle because I just go. Okay. So, but now the much stronger claim, which does not appear as a Gossett exercise, but maybe should, or I think it should just be in the body of the text. Suppose, oh, and I need an extra thing here, which is that
There exists an edge.
No, I want the graph to be connected. Why do I want the graph to be connected? I'm skipping ahead to the next section now. What does connected mean? Simply, a graph is connected if there's a walk between any two vertices, right? So why, say something about bipartite graphs and their connectedness.
It's two separate connected graphs overlaid.
Oh, yeah. Yeah.
That's wrong. Could have disconnected.
Yeah, wait.
You can be bipartite, have no edges.
Can you wait? Can you be a disconnected bipartite graph?
Yes.
What if you have one component which is bipartite and another component which is bipartite? Then it's just bipartite, right? Can you spin the camera over here for a minute? Is that clear? It's like borderline clear, right? If you have some situation and then you just have some other vertices which are like somewhere else, man, it's like, psh, come on. This is like some separate frog population. It's not even like involved in things, right? Then, yes, I guess I should draw the edges first. So if the edges look,
Different population of frogs.
yeah, that's what I was trying to say. Yeah, different population of frogs. Okay. Whoa. Good. Good. Well, if this component is bipartite, and this component is also bipartite, then we may sort of like freely add the vertices of one of the sets of the bipartition to the other ones, and it'll just still be true that the overall graph is bipartite. Follow? So it's like it's sort of trivial. It's sort of not fun or something to consider graphs which are disconnected, because then this just applies to each one of the components. Therefore, I shall restrict myself to connected graphs. Sound good? Okay, good. So someone fix the camera because I messed it up. Good. Woo. So suppose that G is connected. And now what I want to do is to show that, and further, suppose G has no odd cycles. And the claim is that the graph must be bipartite. Okay. Loosely speaking, how would you like to create this bipartition? By the way,
Take the set of all the cycles.
so okay, here's like a crappy, probably a little bit invalid, like sort of talky version of this, right? So suppose that you have no odd cycles, right? So I got some graph. It looks like however it looks, right? It's unclear what exactly is going on. I'm not positive it's bipartite, but like whatever. Okay. So now, am I free to just, and there are no odd cycles, can I just start, like off script now, I have no idea what I'm about to say. Can I just start arbitrarily at any vertex and then label all of its, all the things it's connected with, put them in the other color? Okay, it worked in this case. And then just kind of like alternate or some crap like that?
Yeah.
So say some more things. Does that just like work? Yeah. Hey.
If a graph has, if you take a vertex and you like take all the things connected to it and you put them all in the same group, they're guaranteed to none of them be connected because that would form an odd cycle.
So wait, I guess there's several things to discuss, which is why I'm trying to prove that this is bipartite or something, right?
Well, if
Knowing that there are no odd cycles. So let's start with that.
well, it would be a contradiction if any of the ones you chose were connected because that would form an odd cycle.
And so it's like, right? It's like you're out there and you're a naturalist and you're observing the frogs and you're giving them all cute names like, you know, big red one and like whatever stuff like that, right? And then bumpy head. And then now you're trying to discover like their gender relations, like, you know, if there already is. So you're just like, you know, you're watching, you got a grad student, the two of you are splitting up between around the clock, checking all frog mating patterns, and you've determined all the relationships that exist between this frog population. And you know that there are no odd cycles. Now, does that guarantee that there is some kind of like, you know, frog gender bipartition? This is where we are right now, right? I haven't said anything important yet, mathematically. So, Alana.
I didn't understand, I didn't follow your algorithm for assigning.
Yeah, me neither. So that's why we're trying it again. But first we're like getting the frogs back into it. So now you just start somewhere, right? Anywhere. Observe all the frogs that this frog mates with, and put those in the other. Assign those the other gender. Now, what should we do next? Take all the frogs that this one mates with, and assign it to the other gender, and keep doing that. And I think what Nate was saying is because there are no odd cycles, this can't go wrong. Because the only way for this to go wrong is if there was sort of mating between two people which you had assigned the same gender. But that's just not gonna happen, because for that to happen, there would have to be an odd cycle. That's like, seems like goodish, right? Okay, but what's sort of missing from this a little bit, on a technical level? Is there anything missing? So the rigor is missing, the why that wouldn't happen, the definitions, all this stuff. I'm not even sure that I have, one problem is I'm not even sure I got all the vertices that way or something, right? Like that's another, I think that's like the bigger problem.
But it's connected.
It's connected, but this algorithm was so sort of scattershot, it was some kind of depth first, like just go and just like hope it all kind of comes back or something, right? Does everyone see? I think that's actually the bigger problem, which is, right? Maybe I'm wrong.
As long as
Uh,
every vertex
As long as every vertex is
Between
connected.
all of us, then you're gonna get all of the points this way.
Yeah.
If you do a breath first, you're fine.
All right, good. Let's begin. I think this proof is essentially that same kind of thing, but just made properly. All right, here we go. Choose, so choose a vertex V, little v, from among the set of vertices. All right. Partition G as follows.
Do you like need choice for this? Just gotta wonder.
It's like finite, everything's finite. Everything's finite.
No, but like wondering, do you need choice?
Fine, it's fine. Graphs, finite graphs only. Graphs. Screen that down. Good. Partition G as follows. So much giggling. Oh my god. Alright, good. Let A. So basically, I think this is roughly like kind of what I just said, right? Let A, but it's like a little bit more advanced. Let A be the set of all vertices such that the shortest path from V to V sub I is odd. And let B be the set of all vertices such that the shortest path from B to VI is even.
Can you just define V as V minus A?
You could. You could. I like this. Well, okay. No, that is doable. It's going to be effectively the same thing, but you are right that I need to like mention. So okay, my claim is that this is a bipartition. Okay, first, is it even a partition? And is it even like well defined and all that stuff? Well, like yeah, man, right? Like look, given any particular vertex, just imagine. Remember, the graph is connected, right? Given any particular vertex, there is a minimum. There are only a finite number. This graph's finite. Finite number of vertices, finite number of edges. So given any vertex whatsoever, there are a finite number of paths back to V. Agree? If there are a finite number of paths which get you back to V, then there's like guaranteed to be a shortest one, or two that are the same length that are tied for the shortest. So this is a completely valid definition, because it just is true for any, this is worth talking this out I think, but it just is true for any vertex that there is a shortest path, or a set of paths of equal length, back to this vertex V. And that path, that shortest path is either odd or even. Who is with me? Good, yes.
Can you have a path length of 0?
Can you have a path length of 0? You can.
So V is the set. Okay.
Good, yup. Okay, good. So, my first claim is that A union B is in fact all the vertices. And this is true because, wait, I'm shooting a video. What do you want? Who do you need?
Shooting a video, Mom!
Justin and Cato.
Okay, good. You people, go outside and talk to him in the hallway.
30 seconds.
No, go talk to him in the hallway. So first of all, A union B is V because, as we just said, for every single vertex, it is either in A or B. Because there just is a path back to the little v. And so the path needs to be either even or odd. And of course, it's also true that A intersect B is empty because the shortest path can't be both even and odd. Good? Say good. Okay, and now my claim is that this particular partition, AB, is a bipartition. Okay, and now I'll make the note, which is that since V's distance from V is 0, since V's distance from V is 0, then that automatically places V in B. Okay. Woo! Good. Okay. Good. Now I have to prove that this is a bipartition. How do I prove that this is a bipartition? Well, I have to show that there can't be any edges between elements in the same set. And so what I'm now going to do is I'm going to suppose that there is, I'm going to take any two arbitrary elements of A, and I'm going to suppose that there is an edge between them. And this is going to lead to a contradiction. Gratis. And then I'm going to take any two elements of B and show that that leads, and suppose that B1 and B2 have an edge between them, so that B1, B2 is an edge, is among the set of edges, and I'm going to show that that leads to a contradiction. And if there isn't an edge between any of the elements of A, and there isn't an edge between any of the elements of B, then that shows that there's a bipartition. Cool? Okay. Okay, and there's a picture associated with this. And now also there's like a lemma that I considered doing it in the beginning, but instead we're going to do it now as it comes up. E is the set of edges. So there's just no A1, A2 edge. That's all it is. Okay, so there's like a picture associated with this. Okay, so here we go. So here's what A and B looks like. So here's A and here's B. All right, so if there's an edge A1, A2, why is that a contradiction? Here is this point A1 in A, here's this point A2 in A, and let's recall that the vertex V is in B. So what's everything we know so far? We haven't even used yet our key assumption, which is going to drive the whole proof, that G has no odd cycles. So I know that G has no odd cycles, and I've partitioned all the vertices into whether their shortest path from V is odd or even. Now it's kind of oh, and of course, to add to the picture, I have just assumed, for purposes of contradiction, that there is an edge between A1 and A2. What do you want to say? Yeah, Marie?
If like the length from A1 to B is something, then the length from the other one to it, never mind, it's wrong.
It's only maybe slightly wrong. What can we say about the length from A1 to V? It's odd, right? Yeah, this is of odd length. I think I've done that correctly, right? The shortest, yeah, that's just true. That the shortest path, at least, from A to V is of odd length. Wait, I think I need to be a little bit. Yeah, that's just true. That's just true. Wait, hold on. I need to think for a second.
That is just true.
That's just true.
Because it can't be 0. A1, A2 cannot be B.
Because they're in A.
Oh, okay, no.
You have to assume that A1 and A2 have different path lengths to B.
Yeah.
No, you don't.
No, I don't think so. This, okay, wait. I lost my confidence for a second, but it's back now. So yeah, it just is true that the shortest path from A1 to V has odd length. Just like fact,
There is
right?
a path.
There is a path between, that's worth mentioning. There is a path between A1 and V because the graph is connected. Thus there is a shortest one. The shortest one path must be odd because that's how A1 got in A in the first place, right? Because its shortest path was odd. This is pretty hard.
We don't even care that that's the shortest path anymore.
Well, for purposes of specificity, I care. Okay, but you're sort of right? No, but I do need this path length to be odd.
Yes,
I don't need it to be the shortest, but I need it to be odd. Okay. So yeah, you guys are getting into the subtlety in a second. Okay, and then what about the path? But let's just still speak of the shortest path. What about the shortest path from V to A2? It's also odd. And okay, Alara and them are saying that technically I don't need the shortest one to be odd, I just need there to be an odd one. But the fact that the shortest one from V to A2 is odd means that there is an odd length path from V to A2. Okay, now what have we constructed thus?
An odd cycle.
Almost. It's basically an odd cycle, but not quite exactly totally. Right? What do we actually have? Starting at V, going like to A2, and then to A1, and then back to V. What is that actually? It is a closed walk of odd length. Okay. So what prevents that from technically being a cycle?
Could technically revisit.
Yeah, because you might have done some you may have hit some vertices multiple times or whatever, right? But technically you don't want that. Okay, so just should we just do this lemma right now? Let's go. This is so not my own intellectual work, but I have digested it personally and I'm presenting it. So I guess it sort of is. So lemma, if there is a closed walk of odd length, then there is a cycle of odd length. Okay, and all right. This was all Daniel Zhu, I think. He just spits this stuff out like it's this so obvious. It is obvious in retrospect. Well, okay. Why, if there's a closed walk of odd length, why must there be a cycle of odd length? Well. First of all, because everything's finite, let's just get all the crap out of the way and just take the shortest one. So let W be the shortest closed walk of odd length. Do you see this power move where you just invoke the finiteness to say, well, there just exists a shortest one. And now the claim is that this shortest one, W, is a cycle. Why must the shortest walk of odd length be a cycle? Yes.
Because it's if you went to this point, if you're revisiting this point twice, then you can just leave as if it was the second time, right? Not go if you're in to this point and then to other points and then back and then leave. You just leave.
I think I understood that.
It's similar to what he was saying. If you have a walk of odd length that does repeat a point, then that means that there are two individual closed walks within it, and since it's odd, one of them has to be even, one of them has to be odd.
Yeah, right? So the claim that W is a cycle, the way we back up this claim is suppose not. Suppose that W is not a cycle. Well, if W is not a cycle, then, if it's a closed walk of odd length, but it's not a cycle, what's the only way to not be a cycle? You must revisit a vertex, right? Okay, so then a vertex V is revisited. And now comes the picture, which I saw some of you sort of doing, right? So if there's this vertex V, this is unrelated to the V over there, this is just a lemma. What does this look like? What does this sort of walk, what does this walk, this closed walk of odd length, W, or rather, yeah, W is, we define W to be the shortest walk of odd length. If W is not a cycle, then the closed walk of odd length W must visit a vertex twice, but then this entire walk has odd length. If the entire walk has odd length, then if a vertex is visited twice, then like the path from V to like V the first time, plus the path from V to V the second time, one of them must be even and one of them must be odd. So like let this one be odd and this one be even, but then that's a contradiction, because then this one is shorter. Call this one like call this one like W prime and this one like W double prime. Okay? So wait, hold on. Let me say that all a little bit better. Ready?
Because that's not a cycle.
This picture's also like a little bit weird. Because this is the same vertex, right? What's up? I should make it an 8? Yeah, I think you're right.
That would help a lot.
I think I agree with you. So he says like make it an 8, man. So let this be V. This whole thing is my walk W, and this, let's call this W prime, or let's just do subscripts. Call this like W1 and call this W2. Here's the argument, ready? Take a walk, suppose you have a graph with a closed walk of odd length. Then there has to be a cycle of odd length. Why? Well, take the shortest closed walk of odd length. There's your cycle. Proof. Dude, it has to be a cycle. Because the only way to be a closed walk, not a cycle, is if it's like an 8 type situation, as he says. But if there's some vertex V in W that gets visited twice, right, then that closed walk is really can be thought of as composed of 2 strictly smaller closed walks. And if the total length of this walk is odd, then this partitions that closed walk W of odd length into 2 subwalks, W1 and W2, one of which must be odd and one of which must be even. So without loss of generality, let's say W1 be odd length and W2 be even length. But now, do you see the problem?